Okay, so let's continue again where we left. And this part, I think we covered this one, so we can erase it. We can skip this and just have a look at how we can move forward with this example. Now, let's also look at the major steps that we have to follow. So first of all, we select the pivot row. The second step, we make the pivot element equal to 1. The third step is we modify the rows, the new value of the row equal to the previous value minus lambda times Ri. Ri is the pivot row. Then we finally have to obtain the reduced row echelon form. So this example that we just we were working on, this is called the reduced row echelon form, and it should be an expression where the leading terms are all equal to 1. Now, what we need to define here is that we need to determine what are the leading terms. So, which ones are the leading terms here? They are the ones in red. So the leading terms, they are x1, x2, x4, okay? So here we have x1, x2, and x4. Now, what are the non-leading terms? Can you determine which one are the non-leading terms? And actually, x1, x2, and x4, these are leading, x1, x2, and x4. Okay, so this is where they are. But which ones are the non-leading terms?
X3 and X5.
Exactly. Okay, non-leading terms. These are x3 and x5. Now, x3 and x5, we call these as free variables. Okay, so they are free. They can get any value. So it's the same way where you have a point. But this point, it's a part of a line. So the equation of a line can provide the same no, it's not the same expression. So let's call this free variables. And then we can say that x3, we can write this one as equal to s. And x5, this is equal to t. Okay? So x3 and x5, they are equal to s and t. Why? Where s, what is s and t? S is an element of real number space, so it can be any number from minus infinity to plus infinity. And t is also any number, any real number. Then what we can do from here is that we can try to we figure out that we say that x1, what is x1? x1 is equal to 1 minus x5, right? Would you agree from here? x1 is 1 minus x5. Yeah. 1 minus x5. What is x2? x2 is minus 1 minus x3. Would you agree with this? So we are from here.
Yes.
Okay. Then x3, what is x3? This is equal to
x3.
That's true, is simply s. And what is x4? x4, 3, is just 3. It's a constant, it's fixed. And x5, so we need to write them in this form. x5, this is equal to, what we write x5? It's a free variable, it's t, right? So this is how we can write this one. So I think we have all the information here. What do we need to do next? Next, we can write here that we can write this one 1 minus t, right? And this would be minus 1 minus s. So these free variables, we try to express everything in terms of the free variables. So now, since a lot of things depend on these free variables, I think we wrote these equations here, so we can erase this part. Okay, And these steps, I think they are clear for us. We just use them during the first hour. And let's see here. So we have to carefully monitor this. And we can also say now that x1, x2, x3, x4, and x5, these will be equal to, we can have here a constant term plus one of the free variables s, okay, plus the other free variable t. Okay, so now let's write x1. What is x1? It is 1, this is a constant, 0, minus 1. Would you agree that this is correct? How do we read this? This is equal to x1 is 1 plus 0 minus t1, minus t. Is this, so it looks like it's a good, it's well written. What is x2? And by the way, let's make this for a moment like this.
Professor, where did we get these values from again, please?
From here. x1 is 1 minus t. x1 is 1 plus s0 minus t. So how do we read the top
Okay.
one?
Okay.
The top one, we read it like this. x1 is equal to 1 plus 0 times s plus minus 1 times t. Okay, so that's the same expression. x2, what is x2? We have the constant term minus 1, 0. Then x3 is equal to s. How can you write x3 is equal to s? We just put 1 here, 0, right? x4 is equal to 3. It's a constant term, 3, 0, 0. x5 is equal to t. Somebody tell me what should I write before x5?
0, 0, 1.
0, 0, 1.
0, 0, 1. Okay. So it looks like we have 5 unknowns. Now, what is the union? Union do të bashkësia ose bashkimi I të gjitha pikave që I përshtatet që është zgjidhja e këtij sistemi të ekuacionit. What is the union of all the points that serve as a solution of our system? What is it?
The points where the lies x1 plus x5 equals to 1 and x2 plus x3 equals to minus 1 prehen me njëra tjetrën.
So let's look at this. Remember that we have this equation ax, where a is the coefficient matrix, x is the unknown. This was equal to b or d. Okay. And finally, what did we get for the solution x? For solution x, which is a vector, we find that this is equal to a vector p, okay, which is this constant vector, plus sv, where p is another vector, plus tw. What is this? What does this equation look like?
A plane?
It's a plane.
That's how we express the...
This is a plane, which means that a system of unknowns with 5 unknowns, we end up into finding that the solution is a plane. And how do we notice it? Because we have 2 free variables. If we have 2 free variables, we define a plane. If we have 1 free variable, we define a line. Okay. So, and what is the number of solutions? How many solutions did we find? It looks like we have an infinite number of solutions, right? Because S can be any number. I think we agree on this one. So we don't have one solution. For example, 2x is equal to 6. What is x? Is 1. That's a unique solution. It's only 1. But here, we obtain an infinite number of solutions. Okay? So this is the case. And what is essential, which is very important, is the number of non-leading terms. So if we have x3 and x5, these define really the dimension of the solution. Imagine for a moment that we have three equations, three unknowns, and we get no free variables. Then the dimension of a unique solution would be 0, okay? If we have one free variable, so here we got 2. If we have one free variable, the solution, it will look aligned because the solution would look something like this. Let me find some space. So with two free variables, which are clearly stated here, we get a plane. If we have one free variable, we might get something like this, a constant vector plus s times a vector v. This would be a line, okay? So one free variable produces a line, which is one-dimensional solution. Two free variables, it produces a plane, which is a three-dimensional space solution. Sorry, two. It's a dimension of a plane is 2. But it extends in 3D for sure. Okay, so I hope, is it clear what we did so far?
Yes.
Okay.
Can you explain, excuse me, can you explain one more time how we determine the leading terms and the non-leading terms?
Yes, the leading terms, they were the numbers that were the first in each row. You look at each row and you find the term that is the first non-zero term.
Okay, I understand.
Okay, is it clear? So the first non-zero term is called a leading term. And if you notice, in the first row, we had the leading term, it was x1, and there was also a non-zero x5. That makes it a non-leading term or a free term. Now, let's see. Wait a second. Okay. Anyway. Now, okay, I made what you could do is actually the following. Check for the previous example. Is 1 minus 1, 0, 3, 1 a solution? So if you took notes, can you check if this is a solution which stands for S is equal to T is equal to 0? I should have asked this one before erasing it, but can you answer this? So we had the solution which looked like a plane where S and T are free variables, but S and T is free variables, they could even be 0, right? So if they are 0, the solution would look like this. Can you check if this satisfies the system of equations?
Yes, it does.
Okay, so it is a solution, that's good. Yes, and it should be, but it's good to double check so that we get convinced of the matrix. So let's assume now a system of equations where the coefficient matrix is the matrix 1, 2, 3, 2, 2, 4, 1, 0, 1. Now, as good engineers that you are taking this course, what you can do is initially just look at the equation fast. Do you observe anything for this coefficient matrix?
Square matrix?
There's 0. This is square
It's
matrix.
3 by 3, the first thing. What else?
There's a 0 in it.
Of course, there's a 0. It is almost half sparse, so it's a simplified one. Anything else?
So we can divide by 2 the second row.
Yes, you can. Well, let's try the first.
One of the leading terms is 1.
Okay, that's also something else. Anything more?
Third row is the sum of the two first rows.
So how did we solve the example in the previous hour? We wrote the coefficient matrix and we merged, okay, with the original matrix the answer vector, okay? This merging of these two matrices, or the coefficient matrix with the answer, we call this augmented matrix. And we denote it like this. We put here the coefficient matrix A, we put a line just to lead the eye, okay? It's not there, but we write here the B. But this is the augmented matrix. And let's write this, and we get the following. We get 1, 2, 1, 3, 2, 5, and we do the rest 2, 2, 0, 3, 4, 1. Okay? So, now, once you look at these equations again, what do they say to us? How do we read the first equation? The first equation is x plus 2y plus z, this is equal to 3, 2x plus 2y, this is equal to 2, and 3x plus 4y plus z, this is equal to 5. Do you see anything else in these expressions?
Somebody said that the last row is the sum of two others. I didn't say it, somebody else said it.
That's true. This is the most essential. Sometimes it's hard to see when the rows or when the equations are dependent on each other, or which is defined as one row can be expressed as a linear combination of the other rows. It's not always easy to see it, but here you correctly observe that equation 3, okay, equation 3, this is equal to equation 1 plus equation 2. Equation 2. So if this is the case, what can we say? So the moment we see this, you said initially that we have, it's a matrix 3 by 3. What do you observe else? We have 3 unknowns. Okay? We have 3 unknowns. But if we have 3 unknowns, how many equations do we have? Well, we have 2 equations. We don't have 3. Why do we have 2? Because the third one is depending on the first 2. So the third equation is not telling any new information. It's already reported here and here, right? Because we can see here, x plus 2x is 3x, 2y plus 2y, 4y, z, and 3 plus 2 is equal to 5, okay? So we have 3 unknowns, we have 2 equations. If we have 2 equations, then we should have one free variable. If we have one free variable, okay, what does free variable mean? It is a non-leading term. Then what should be the solution? Okay, solution, it should be equal to P plus a free variable S times V. What is the solution? What does it look like?
It's a line.
A line.
That's correct. It's a line. What is the number of solutions? It's an infinite number of solutions. So it does not have a unique solution. It has many solutions. So this is the answer. Is it intuitive? Is it clear? Yeah, I think it should be okay. So what we do here is that we try to obtain the reducer row echelon form. So how do we get the reducer row echelon form? So if you allow me, I can erase these expressions here because we can also read them elegantly from here. So first we define a pivot row. Which one is a pivot row?
The first one.
Row 1. Okay, that's good. So if this is the pivot row, then what is the next step? The next step is we apply these operations. We say row 2 star is equal to row 2. How should we modify row 2?
Minus 2R1.
Minus R1.
That's correct. So we need to make these two 0 using this, right? Using this pivot element or using this reference element, we need to make, so it's R2 minus 2R1, right? How can we make this 0, this 3? Row 3 star is equal to row 3, then what?
Minus 3.
Minus 3.
0, 1. Then, let's write this down. 1, 2, 1, 3, we get, okay, somebody help me here. So what should we write here?
0. Minus 2.
Yes.
Minus 2. Minus 2.
Minus 2.
What then?
Minus 4.
That's correct, minus 4. What about here? So we have to make 0 distinctly, which is that
0.
what's that?
-2.
-2.
-2.
-2.
-2.
Yes,
And -1.
-4.
-4. Okay.
-4, yes.
So with a single run of the using the pivot row, which is row 1, we notice that this equation is equal to this one. Okay. So what is the next step? The next step is to do the following. We say here that row 2 is the pivot, and then the third equation would be this one. We say row 3 star is equal to row 3, okay, minus row 2. And this should end up all in zeros. Would you agree with this?
Yes.
Okay, but so I mean this is almost obvious, or we can use a more gradual step, which could be the following. The next step could be this: we do row 2 star. This is equal to row 2 divided by -2. Okay, and then if this is so, I hope you understood this part, and let's take this part out. Then we get the following: 1, 2, 1. This remains as 3. This is 0. If we divide by -2, we get here 1, 1, 2. Then here we get 0, -2, -2, -4. So then, if we are at this stage, we again make row 2. So we said that we can do the following. We can say that row 3 star is equal to row 3 plus 2 row 2. Would you agree with this? Because how can we make this 0 if this is the pivot element? Let's not forget that it is very essential that we have these leading ones equal to 1. Sorry, leading terms equal to 1. So, ne mund ta mbanim këtë minus 2. Por është më mirë ta bëjmë mish. Do shikojmë sepse është kaq e rëndësishme. So, I think it is almost obvious that -2 plus twice times 1, we should get a 0. So if we follow this operation, most probably you might agree that we can make a 0 right away. Okay? This is 0, 0, 0. Then what is the next step? The next step is to
make the numbers above the diagonal 0.
Exactly. So the numbers above the diagonal, we try to make those 0. So this part we achieved it. We did it. Now we want to make those zeros. How can we do it? We have to determine a pivot row. Pivot row, this cannot be made a pivot row, the third row. So we have to make the second row as a pivot. If this is a pivot, what is the equation that we can use?
R1 star equals
Yes.
R1 minus R2.
R1 minus R2. So, how does it, why would this help?
Because you turn 1 into 0.
Okay, but what if, let's say also the following. So once we do this, we try to make initially, you are very right. So in that case, we make this zero.
We can remove R1
But
minus
it could be better.
R2.
It could be better if, allow me for a moment, it is better if we make zeros using the leading element, okay? So let's try to produce zeros using this number. So if we try to make zeros above this number, this is possible, but probably row 1 star equal to row 1 minus 2 row 2. This is a better choice, okay? This is a better choice because we have to make zeros from the leading terms, okay? Your initial proposal would make this 0, but we'd rather make this one. So if we pick this one, when compared to this, we obtain the following. We get 1. Let's add it like a 0, 0, 0, 0. This is 0, 1, 1, 2. And then we get the first row minus twice the second one. This is 1, 2 minus 2, 0. 1 minus 2, minus 1. 3 minus 4, minus 1. Okay? So this is
Professor,
all.
why don't we just get rid of the third row?
You mean to get rid of this 0, this one here?
No, the third row. Just the third row to get rid of the 0.
Yes, yes, we can. I mean, I can do it, but some of you in the class might get confused, but we can do it. It's gone. You can find it in the history books or in the museums. Okay, so if you miss it, that's where you can find it. Or you can just scroll back into the YouTube video. So, in the recording. So this is what we have now, okay? And then we look at this expression, and it looks like we cannot make it anymore, we cannot simplify it further, because the pivot elements are these. And anything above and below of these, they are zeros. So we cannot improve them anymore. So these are zeros. So at this stage, we have to determine what are the leading terms, okay? What are leading?
x1 and x2.
X1 and X2.
X1 and X2. The multi-theta, we can also call them X, Y, Z, but X1 and X2. What is a non-leading term or a free term?
x3.
X3. Okay, then if this is the case, we can write the following. We can say that X3 is equal to S is a constant, okay? And S, it's a number, it's a member of the real number space. So it's any real number, including the 0. Then we can get the following. We can say that.
Position 1 filling x, y, z now.
Sorry?
Didn't we write them firstly as x, y, and z, not x1,
Yeah,
x2?
you are right. They are equivalent, okay? We could use either one. Let's go with X1, X2, and X3. They are equivalent. But let's now try to write what is X1. X1 from the first equation is equal to what? This is minus 1. Actually, or let's write them here. This would help us. This is X1 minus X3. This is equal to minus 1. And X2 plus X3. This is equal to 2. They are not very difficult. At the same time, since we said here X3 is equal to S, we can write the following. X1 minus S, this is minus 1. And X2 plus S, this is equal to 2. I mean, they are all the same thing. So if we continue here, X1 is equal to minus 1 minus S, right? What is X2?
Minus 1 plus
Plus
S. Plus.
X3.
It's plus S, yes. X2 is equal to what?
2 minus x3.
2 minus S.
2 minus S. Okay, so X3 is a free variable now. What is X3? Just S, okay? So then, so we are trying to, in fact, we could write it fast, but it's always good to do it step by step so that we don't miss anything. And now let's write X1, X2, X3. This is the vector. This is equal to a constant term, okay, plus the free variable S times the direction, okay? So this should be the answer. Now, what can we write here for X1? What is this initial term?
Minus 1.
Minus 1.
Right?
1.
1, okay. What about X2?
2.
2 minus 1.
Okay, what about X3?
0.
0, 1.
0 and 1.
1.
Okay, so that's true. So then we can say that the solution X, which is so now let's not forget that X is a triplet. There are three numbers which can correctly define the solution. This is equal to P plus SV, right? So this is a line, right? Apparently. So when we looked at this equation, right, at the first moment we wrote it on the board, you said that the third equation is equal to the second equation plus the first. So we have two equations. That means that we have one free variable, and then if you have one free variable, the solution should look like this. And this is what we at the end found. So let's check. Wait a second. Okay. X1 plus 2x2 plus x3, this is 3. 2x1 plus 2x2, this is equal to 2. And 3x1 plus 4x2 plus x3, this is equal to 5. So these were the initial equations, right? We write this from the matrix representation. So let's check. If we set S equal to 1, what is the solution? If S is equal to 1?
0, 1, 1.
0, 1, 1. Okay. If it is 0, 1, 1, let's check if they satisfy this expression. I mean, these initial equations. Let's not forget these were the initial equations. So 0, 1, 1, what do we get? We get 2 plus 1 is equal to 3. That's correct. Then x1 is 0. We get 2x2. 2 is equal to 2. And then, so let's not forget that 0, 1, 1, this means x1 is equal to 0, x2 is equal to x3 is equal to 1. That's what we're trying to substitute here. And we get 4x2, which is 4 plus 1, this is equal to 5. So yes, we confirm that substituting a specific value for s, this would satisfy our equation. Okay? Okay, so everything looks fine. And so far, we solved the system where the solution was a plane, a two-dimensional structure. We solved the system where the solution is a line. And now, let's see what can happen if we change just one number. Okay? So, what do we see from here? 3 plus 2 is equal to 5, right? Let's make 3 plus 2, let's make this 4. No, sorry. We don't make 3 plus 2 is equal to 4. But let's change this. If we make this 4, what can we say? This is 4. We can say that equațiunile trei, nu știu equațiunile 4 Okay, so the third equation is not anymore the first one plus the second one, right? So then, what would be the reduced row echelon form? So let's not forget, we're trying to obtain, so we know what this equation is about, but we're trying to obtain reduced row echelon. We're trying to obtain this. Then, what do we get? We follow the same equations like here. So we get 1, 2, 1, 3. Then the second one minus twice the first one, so we get 0, minus 2, minus 2. What is this? Minus 4. Now, you can help me here. So this one minus 3 times the first one. 3 minus 3 is 0. 4 minus 6 minus 2. 1 minus 3 minus 2. And what do we get now? What do we get now if we repeat this equation?
Minus 5.
It's 4 minus 5, that's correct. Okay. Then, what is the next step that we need to do? Let's erase this.
Divide by minus 2.
Let me write these equations here. So the next step we need to do is that we divide by minus 2, right? And what will this come? Can I write this right away? 1, 1, 2, because it's almost obvious. Let's write this one. 1, 1, 2. So we had the leading element 1, now we have a leading element 2. So what should be the next equation? The next equation can be, can you help me here? Rho 3 star is equal to rho 3 plus 1.
Plus minus 2 rho 2.
Say it again, plus?
Plus 2 row 2.
Exactly, plus 2 row 2. So it's minus 2 plus 2 фичная нижи, that's 0. So then we get the following. We get 1, 2, 1, 3, 0, 1, 1, 2. And let's see here 0. We get minus 2 plus 2, 0. Minus 2 plus 2, we get 0. And what do we get here? Minus 5 plus 4, we get minus 1. So what do you observe here?
How do you
Still, we
define-
have
Okay, this
infinite
has no solution.
solutions.
Say it again.
We're still gonna.
We observe this interesting expression.
We have
Can you say it has no
solutions.
solution, this system?
Say it again.
This system has no solution. Can we say that?
Exactly. So apparently we have no solution. So no solution. So far, what did you see today? So we noticed that it is possible for a system of equations that we have zero solutions or no solutions. Okay, no solutions. And we have seen also the case when we have an infinite number of solutions. In fact, we were not lucky to get an example today where we have a unique solution. Would you consider the possibility of having a system that has only one point, only one solution? So we saw this. I'm asking you whether this exists, and I'm asking you if you have any system which has three solutions.
Does this one solution case exist
No.
when we have 3 planes?
Oh, it can be. Can be.
But, so yes, this is true. It is, I put a question mark, but for sure, there is a case when we have a unique solution or only one solution. But now I'm asking you, would you expect a case or a system which has exactly three solutions?
No.
I think it can be.
Are you saying no?
Well,
Yeah,
S,
I think no.
S should take only one value to have only
It can
three
be a
solutions.
point or a line. I don't think it can be.
It has to be a
nothing
point.
complete.
In the plane, 3D plane, it has to be a point.
So you are saying that the solution is going to be, it can be no solution, nothing. It can be a point, that's good. It can be a line, that's also good. It's a plane. But, so you are saying no to this. Okay, let's keep with this no. Let's say no for now. But we are going to provide more details in this course, okay? But it looks like a good option. It looks like a good choice when you say that there is no solution. But we're going to see this in detail in the next hours. Okay. So far, do you have any question? Is everything clear?
No.
Everything clear.
Okay. Thank you very much. Then let's see you in the next session.
Thank you.
Bye.
Bye.
Bye.